Welcome, welcome. We're beginning chapter 5, where we're going to start to look at entropy and the remaining laws of thermodynamics. So we start off this chapter, a quick reintroduction of S. So as long as energy is conserved, so remember our first law of thermodynamics, that energy can only be transferred, not created or destroyed. The question becomes, why doesn't a temperature gradient form? Why can't heat segregate itself to one side of an iron bar? Why don't gases shift around in the air such that a pocket of vacuum forms? Why can't there be a region of no air? I mean, it's good that this doesn't happen. You don't pick up a warm iron bar and suddenly find out half of it is ice cold and the other half is going to melt your skin. You don't walk through the air worrying about whether you're going to die suddenly because you walk into a pocket of vacuum and there's no air. But why don't these things happen? These are unnatural transformations, and they're called non-spontaneous processes. Doesn't mean they can't happen, but they're unlikely to occur within a human lifetime. So they're not going to happen without some sort of outside force. They're highly improbable. Now, entropy can be used to predict the spontaneity of a given transformation. So looking at entropy on a big scale, it's kind of hard to really quantify this. But when we look at it on a microscopic scale, it's a lot easier to understand. Each atom or molecule has certain degrees of freedom. We talked about this before when we talked about heat capacity. We have some translational degrees of freedom, some rotational, and some vibrational. We also have some electronic, where they can jump between excited states or relaxed states. All this can be calculated via quantum mechanics. And in fact, this can be physically quantified using the equation S, or entropy, is equal to Boltzmann's constant and the natural log of W, where W is the number of quantum states allowed within a macroscopic system at a given energy. So if you're just looking at one particle, where's this particle? Is it in the box? Is it rotating? Is it facing this way? How many different possible situations can this one particle have? That's its different quantum states. Now, as we add more particles, we can have a greater amount of quantum states, and the number of quantum states goes up, and thus the entropy. Now, we're not going to bother to actually calculate W. Just know that W is calculable. Because it's calculable and constant for a given system and temperature, we can have a standard entropy and describe the entropy of a system. So what you have here is the Carnot cycle. Entropy and the state function were first discovered due to the study of engines. How did we make an engine run efficiently? A simple engine, we need two heat reservoirs, a hot reservoir and a cold reservoir, and a chamber of ideal gas hooked up to an eccentric. The eccentric is that rotor that doesn't just go up and down, but goes around and around the circle as the pole goes up and down. So the eccentric is there to generate work. So while work can be converted to heat with 100% efficiency, heat cannot be converted to work with 100% efficiency. So looking at here from step 1, so position A, the chamber is fully compressed. It is pushed against the hot reservoir. And an isothermal reaction happens, where heat from isothermal temperature remains constant. So heat flows to the ideal gas, changing the pressure and the volume, allowing it to expand at a constant temperature. And so we have a hot expanded gas. Step 2, so we ended up at B. Step 2, we picked the chamber away from the hot reservoir and allow it to keep expanding in an adiabatic fashion. So keep expanding until so it's going to cool down a bit as it expands and releases some of the pressure. At that point, we're at step C. Point C, step 3, we have an isothermal compression. So it's pushed onto the cold reservoir. It completely sucks out the heat, allowing this to start cooling down and contracting a bit. It gets to step D. At that point, we lift it off the cold reservoir and let it keep adiabatically compressing till we get back to the original starting point. And then we press it onto the hot reservoir. Do it again. So on the first step, it's absorbing heat, then adiabatic expression, heat is being converted into work, for the isothermal compression, heat is leaving, being absorbed, and then heat is being which one's the heat converting to work? Work is converting into heat. So, but essentially we get back to the original spot where it's hot. So now the engine is only useful if we can take more work out than we put the work in. Which is why we separate the isothermal sections from the adiabatic sections. If we had just 2 isothermal sections back to back, it would look like, and then right back. And you'd get no energy out because it's a straight line. That's something more like, and then it goes straight back. Well, I'm not doing a very good job, but it's essentially a straight line where the area within that cycle, the area within that curve, is essentially related to the energy is. And if there are 2 lines, area between 2 lines is 0. 2 overlapping lines. Now this reversible cycle is called the Carnot Cycle after a French engineer who studied. But because at the end of the cycle, the ideal gas returns to its original pressure, temperature, and volume, the internal energy of the system is 0. Now this can be accomplished by transferring heat and work to and from the surroundings. So there's work in 4 different steps, and that's going to be total work of the cycle. But there's heat in only in steps 1 and 3. The step 2 and 4 are adiabatic, which means heat flow has to be 0. So for this to be true, that the total internal energy change is 0, work and heat must cancel each other out. So the total work of the cycle must be equal to the sum of the heat from steps 1 and 3. Now, the work produced by the engine is the result. Efficiency will be defined by the heat flow in these 2 steps. Now, if the heat flow in and out are equal, then no work will be done. However, to be 100% efficient, no heat flow would be able to leave in step 3, meaning all heat was converted into work. But that's not really going to be the case. So we can say the efficiency is the total sum of all heat divided by the heat of step 1. Or essentially you can say 1 minus heat of step 3 over step 1. But efficiency will always be dependent on the 2 heat flow steps. Now, so here's where we have the second law of thermodynamics being introduced, which shows that it is impossible for a system to undergo a cyclic process whose sole effect is to pull heat from only a hot reservoir, converting it into an equal amount of work. Now, this definition is a little different from how we may have discussed this in general chemistry. But so, alternatively, it's impossible for the system to undergo a cyclic process whose sole effect is to absorb heat from a cold reservoir and emit an equal amount of heat into a hot reservoir. Essentially, it is impossible to generate a perpetual motion machine or create an engine that runs with 100% efficiency. We cannot get something that's going to use its energy to power itself and generate more energy than put in. We also cannot create an engine that runs, essentially we cannot get something that absorbs all the heat without some loss. So, looking at this, we want to prove what is the work done by a Carnot cycle of 1 mole of CO2 gas, and then show the efficiency. So we have A, B, C, D, a pressure, we have a volume, we have a temperature. Temperature of A is 300. Temperature of B is 300. Temperature of C is 200. Temperature of D is 200. Volume is 2. B is 10. We don't need really the pressures for each of these guys because none of these are undergoing an isothermal, isochoric process. So I'm going to actually leave out the pressures. We could calculate the pressures using PV equals nRT, but I'm going to leave that out. Why do any more work than we physically have to? But in order to solve this, we need C sub V, we need gamma. So C sub V is 37.14 minus 8.314. We're going to round that to 28.83. And gamma would be C sub V, or C sub P divided by C sub V. 1.28. Okay. Now to get volume for C and volume for D, we're going to have to use the adiabatic change. B to C is adiabatic change, and D to A is adiabatic change. So 200 divided by 300 equals 10 over x. 1 minus 1.28 is negative 0.288. To get rid of that, you have to invert that to get to the net power. So 200 divided by 300 raised to the power of 1 divided by negative, raised to the power of 8 times 200, 300 raised to the power of 8. No. So 200 divided by 300 raised to the power of 1 divided by negative 0.288. Then multiplied by 10, we get 40.87. Now the other one. We'll still keep with the 200 over 300. Now 2 over x, 288. So instead of multiplying by 10, multiply by 2. You get 8.17. So you can, from there, you can calculate your P's if you so want. But we can, from there, calculate our work, our heat, and our efficiency just fine. All right. So our work on steps 1 and 3 is going to be negative nRT, right, ln VF over VI. So negative 8.314 times 300 times ln of 5. So that's negative 4014. Work 3 is going to be negative 8.314 times 200 times ln 8.17 over 40. 0.87. Yet positive 2676. Now you'll see work 2 and work 3, well, work 4 will not matter. Adiabatic steps. Now, because there's no heat flow, you can calculate the adiabatic work from just the internal energy change. So 28.83 times 100 times negative 100 for that first step. So negative 2883. And this is going to be 28.83 times positive 100. So the work on these two steps will cancel out. So negative 4014 plus 2676. The work of the cycle is negative 1338. Now, easy way to do this, the heat of the cycle. Step, you don't need to consider step 2 or 4, because heat is 0. Well, the heat of the cycle, 37.14. Well, you could say heat of the ice. Well, you still need to do that. So heat of the isothermal process, just the opposite of this. So positive 4014 and negative 2883. That's going to be positive 1338. Right. So we got the heat, and now the efficiency is just 1 minus the 1 minus the quotient of those two. So 1 minus 2883 divided by 4014. So efficiency of 0.28. So should I get, oh yeah, I put in the wrong number. Efficiency of 33.33. So essentially being this engine is 33% efficient at converting heat into work. Now, for this taught you something, if you felt you learned something, please like, please subscribe. See you later.